clipped classroom video for Maths AS Unit 1, Polynomials and Higher Derivatives. In the previous video we looked at the gradient of a line, and of a quadratic, and of a relatively simple cubic. So we'll have a little reminder here, look at the gradient of a slightly more complicated cubic. So we have y equals x cubed plus 2x squared minus 4x plus 1, and we need to find dy by dx from first principles. And that means using the limit as delta x tends to 0 of f of x plus delta x minus f of x divided by delta x, or equivalent. So let's have a look. First of all, we're going to work out what f of x plus h is. We can use h or delta x. You'll remember from the previous video and previous work. And you'll notice I've spread it out, and as we proceed you'll see why. So if we put x plus h into that equation, the x cubed becomes x plus h cubed, the 2x squared becomes 2 times x plus h squared, etc. And then we have to expand each of those bits. So x plus h cubed is x cubed plus 3x squared times h plus 3x h squared plus h cubed. X plus h squared becomes x squared plus 2xh plus h squared, and that's still all times by 2. We can multiply out the next bracket, so that gives us minus 4x minus 4h. Remember, the minus combined with the plus h becomes a minus 4h. And then we've got our plus 1 at the end. And then finally we'll multiply out that middle bracket there, and that gives us that very long thing, which I'm not going to read out. So that's our f of x plus h. We're going to need to subtract from that f of x. So we'll write f of x, and now you can see why I've spread it out, because it makes it very easy to see what's happening. So when we subtract to get our f of x plus h minus f of x, then the x cubed will disappear, leaving us the 3x squared h plus 3x h squared plus h cubed. The 2x squared will disappear, leaving us 4xh plus 2h squared. Minus 4x, take away the minus 4x, that means that disappears, leaving us with minus 4h. And the plus 1 take away plus 1 also disappears. And then we have to divide everything by h. So those plus noughts are telling us where those subtractions happened. And we don't need to write them, so I've just put them in to show you that. The next thing we can do is divide through by the h. This is how this works. All the terms without an h in them have disappeared through the subtraction. So the 3x squared h becomes just 3x squared when we divide by h. 3xh squared becomes 3xh, and so on. So we've done all that cancelling, and that leaves us with dy by dx being the limit as h tends to 0 of what's left, which is 3x squared plus 3xh plus h squared plus 4x plus 2h minus 4. Now, when we let h tend to 0, those h terms, the terms with h in them, will all go to 0, and we're left with the answer, which is 3x squared plus 4x minus 4. We've done a few of these now, so we can possibly see that there's a general rule. So what have we seen so far? So we have our y and our dy by dx. Remember that if we have f of x, we sometimes call the dy by dx f dashed of x, so that's the gradient function. If y is x, then the gradient of that is 1. If y is x squared, the gradient is 2x. If y is x cubed, the gradient is 3x squared. So, can you see a pattern? Well, we can see 1, 2, 3 happening, we can see x and then x squared happening, but if we add these symbols in, we can very easily see the pattern. So x to the power of 1 is just x, so that red 1 that we've added doesn't change anything, but we can see that we're actually going x to the power of 1, then x to the power of 2, then x to the power of 3. And in the dy by dx column, the added x to the power of 0 is just equal to 1, because anything to the power of 0 is 1. So it doesn't change it, but it does mean that we can create the pattern. And similarly with the x to the power of 1, the extra red 1 in the second line there for the dy by dx column doesn't change it, but we can see that we now have, for the coefficients there, a pattern of 1, 2, 3, and for the powers a pattern of 0, 1, 2. So that leads us to a general rule, which is that if we have y dy dx, f of x, f dashed of x, then if we have x to the power of n, then when we differentiate that we get n times x to the power of n minus 1. If x to the n happened to be times by a constant, so if we had a, which stands for any number, times x to the power of n, then the gradient function would be a times n x to the n minus 1. To find the derivative of higher powers of x, we can use the binomial theorem if we needed to do it from first principles. For examination purposes, we only need to be able to do it up to x cubed, but we do need to know that rule. So I've shown you a pattern. The pattern suggests that rule, but you're having to accept that that rule is true. But if you want to prove it, you can use the binomial theorem for that. So let's have an example. If we have the function y equals 7 times x to the 8 minus 3 times x to the 7 plus x minus 8, then when we differentiate, first of all I'm separating it because we need a bit more room. So dy by dx, well, the 7 we keep. From the x to the power of 8 we bring the 8 down, so that gives us 8, and then we have 8 minus 1, so that's just using the general rule from the left of the screen. For the 3x to the power of 7 we get 3 times 7 is brought down, the original power, and now x is to the power of 7 take away 1. We know that the gradient of x is 1, and we know that a constant will just move the graph up or down. It won't change the gradient, and so we have take away nothing at the end there. We can then tidy that up. So 7 8 is 56, 8 take away 1, you'll be amazed to hear, is 7. So for the first term there we have 56x to the power of 7. Second term gives us minus 21x to the power of 6, and there's our plus 1 as well. We've only seen that for integer powers of x, in fact positive integer powers of x, but it turns out that we can use this rule for any rational power of x, so that means integers and fractions. So find dy by dx if y is equal to the square root of x. Well, the first thing to do is we can change the square root of x into a rational power. The square root of x is the same as x to the power of a half. To differentiate, we bring the half down and we subtract 1 from the power of a half. So that leaves us with a half times x to the minus a half. If we want x to the minus a half, well, to the power of minus means that this term goes on to the bottom of the fraction, and to the power of a half means it's a square root, so that gives us 1 over 2 root x. Slightly more complicated one here. So if f of x is 2x to the power of a third divided by 5 plus 5x to the minus 4, to differentiate, well, first of all, as I have done before, I'm separating them out to give myself room. So f dashed of the first term, well, we have to keep our 2 over 5, which is what the x to the third is being timesed by. Then we bring our power down, which is 1/3. Then we do x to the power of 1/3, take away 1. For the second term, we have our original constant of 5. We bring a minus 4 down, and we subtract 1 from the minus 4. Then we multiply things out, so 2 over 5 times 1 over 3 is 2 over 15. A third, take away 1 is minus 2/3, so that's our new power for that term. And for the second term, we have plus 5 times minus 4, which is minus 20, and then the minus 4 take away 1, of course, becomes minus 5, so that's minus 20 x to the power of minus 5. The second derivative, so what does that mean? Well, if we want to find the gradient of a gradient, or the derivative of a derivative, then this is called helpfully the second derivative. So the derivative itself can be called the first derivative, and then if we differentiate that, we get the second derivative. And an example of this in action, as it were, or in application, is that if we have a distance time graph, then the gradient of that graph gives us the velocity, and acceleration can be found from the gradient of a velocity time graph. So if we instead do the second derivative from the distance time graph, that will give us the acceleration. Now, the second derivative, we need to have a notation for that, and so we have this symbol here, and we say it d2y by dx squared. That's a convention, and as your mathematics develops it will make more sense, but for the moment you just need to know that it's said d2y by dx squared. So let's have a look at an example. Find the second derivative of y equals 5x cubed minus x plus 2. So if we differentiate, we have our 5, and then for the x cubed we bring the 3 down and subtract 1 from the 3, which gives us 3x squared. The minus x differentiates just to minus 1, and the plus 2 differentiates to 0. So tidying up, that gives us 15x squared minus 1. For the second derivative, we have to just do the derivative of the first derivative. So we keep our 15. We bring a 2 down from the x squared and subtract 1 from the 2, which gives us 1. And instead of writing 2x to the power of 1, we just write 2x. And when we differentiate the minus 1 there, that becomes 0. So in this case, the second derivative is 30x. Another example, slightly more complicated, and this is our example from before. So we have f of x equals 2x to the third over 5 plus 5x to the minus 4. So we already know that the derivative, the first derivative, is 2/15 x to the minus 2/3 minus 20x to the minus 5. So we then differentiate that again. The notation here is f double dashed, and we have our 2/15 as our multiplier there. We bring the minus 2/3 down, we subtract 1 from minus 2/3, which gives us minus 5/3, because 1 is the same as 3/3, and if we take away 3/3 from minus 2/3, we end up with minus 5/3. For the second term, we have take away 20 already. We bring the minus 5 down from the power, and we subtract 1 from minus 5, which gives us minus 6. Just a note, if y is f of x, we can use f double dashed of x to denote d2y by dx squared. If time is involved, it was mentioned earlier that dy by dx can be called x dot. Well, for the second derivative, we sometimes use x double dot. Anyway, that f double dashed of x needs tidying up, and we get 2/15 times minus 2/3 is minus 4 over 45, x to the minus 5/3, and minus 20 times minus 5 is plus 100, and that's times x to the minus 6.